What if what we see is not reality? Then where does the true reality exist? To explore this simple yet profound question, I will break it down into 8 layers, guiding you step by step to understand the essence of reality. Let's start with an apple and an extremely sharp knife. You hold the knife, and with a swift cut, the apple splits in half. Then you cut it into 4 pieces. Then 8. With each precise slice, the apple's flesh becomes more and more fragmented before your eyes. However, by the 14th cut, a distinct rectangular pattern emerges. Suddenly, you realize the smooth flesh of the apple is actually made up of countless plant cells intricately arranged. You continue cutting, slicing the cells into smaller and smaller fragments. After another 8 cuts, the cells have been reduced to complex molecules of carbon, hydrogen, and oxygen. A few more slices, and the apple has transformed into 10 to the power of 27 individual atoms. You pause, a question forming in your mind. Is this the limit? Can it be divided no further? Yet, your knife is sharper than you imagined. So, you boldly take on a new challenge: the atom itself. You peel away the electron cloud, revealing the seemingly empty structure inside. But at the heart of this near emptiness lies a tiny atomic nucleus. It is a million times smaller than the original apple. But you do not stop. Instead, you press forward, determined to cut even further. Under your knife, the atomic nucleus splits into protons and neutrons, which, in turn, break down into quarks and gluons. At this moment, you find yourself in a surreal subatomic world. Here everything is governed by uncertain probabilities. That apple, it was nothing more than a fleeting ripple on the vast ocean of reality. You feel as though you've finally reached the fundamental building blocks of the universe, perhaps reaching the ultimate limit of division. Yet, some believe you can go even deeper. After over 100 more cuts, the point-like quarks and electrons might reveal their true nature as vibrating strains, dancing in another dimension. At this extremely microscopic scale, space and time may take on a block-like structure, becoming indivisible fundamental units. Or perhaps, all appearances of reality will simply fade away. We may discover that the universe is actually a simulated world running on a higher dimensional computer. Or, our 3-dimensional existence may be nothing more than an illusion, with everything we know and cherish being mere projections on a holographic screen. Even more astonishingly, perhaps all of this is just a pure mathematical construct. 233, from the vast cosmos to the tiniest particles. Without exception. But which of these is the truth? And how can we ever be sure? For thousands of years, humanity has worked tirelessly to uncover the mysteries of reality. We must bravely dissect the universe, asking deep and complex questions. Does this apple truly exist? You can touch it, smell it, and taste it. You can admire its vibrant green skin under the sunlight. Without a doubt, the apple exists. But what does real truly mean? And what exactly is reality? To our ancient ancestors, reality was undoubtedly straightforward and self-evident. From the vast plains of Africa to the nomads of the snowy north, reality was everything they could see, hear, touch, and taste. Reality was right there, tangible and undeniable. In their daily struggle for survival, these early humans likely had little time to deeply contemplate the nature of their world. However, as human intelligence evolved and our thoughts expanded, our understanding of reality began to shift. Evidence suggests that around 100,000 years ago, humans started burying their dead. What went through their minds as they said their farewells? We may never know, but perhaps they envisioned a world beyond this one, a life after death. These burial rituals reveal the depth of human thought, showing that reality is far more than what the eyes, ears, or nose can perceive. The idea of souls, gods, and unseen yet powerful forces gradually emerged. Along with it came the search for meaning and purpose. The gods not only granted us apples as delicious fruit, but also spared us from having to question the deeper mysteries behind them. These answers lay beyond the reach of human thought, existing only within the minds of the gods. Plato, a great philosopher of the ancient world, lived in Athens during the 4th century BCE. His real name was Aristocles, but his nickname, Plato, meant broad or wide. The material world deeply puzzled him. Where do objects get their physical properties? Whether it was the green of an apple's skin or a dog's 4 legs. These questions fascinated him. Plato firmly believed that the world we live in is not the real world. To explain this idea, he introduced the famous allegory of the cave. He asked us to imagine a deep cave, where a group of prisoners has been chained since birth, able to see only the wall in front of them, having never left the cave. They have no experience of the outside world or true reality. The only thing they can see is the flickering shadows on the cave wall. These shadows are projections, cast by the sunlight outside as people move about. To these prisoners, the shadows are their entire reality. How could they possibly understand the invisible world beyond the cave? How could they grasp what is truly real? But let's take it a step further. What if the shadows weren't even real projections of the outside world? What if tricksters built a fire at the cave's entrance, casting artificial shadows by manipulating puppets? Now, instead of ordinary figures, the prisoners would see monsters, battles, castles, and kings. Faced with this new reality, how would they react? To them, the images on the wall would still be reality. These strange new stories would seem just as real as the previous shadow figures. Monsters and battles would exist as absolute truths in their world. Through this allegory, Plato urged us to reflect. Are we, too, like these prisoners? Is the reality we experience every day merely a shadow of the true world? Could our imperfect world be nothing more than a blurry reflection of a perfect one? In Plato's view, our perceptions are merely shadows of the true reality. Given what we know today, this idea seems remarkably prescient. However, in the journey to understand the nature of reality, this was only the beginning. To uncover the mysteries of the universe and seek the ultimate truth of its nature, the answers do not lie in the hands of gods or ancient philosophy. Instead, we must delve into the fundamental building blocks of matter, time, and space, using the power of scientific exploration to grasp reality. As we embark on this journey, reality quickly begins to reveal its strange and mysterious side. Let's turn our attention back to this apple. One of the most striking features of a ripe apple is its colorful skin. But where does this color come from? An apple is composed of water, sugars, and more complex structures. So why do we see it as green? To answer this, we must explore the very nature of color. Artists know that mixing different pigments creates new colors, with red, green, and blue being especially crucial. Thomas Young proposed that the human eye contains 3 types of light-sensitive cells, now known as cone cells, each responding to red, green, or blue light. The degree to which these cells are stimulated is transmitted to the brain through the optic nerve, blending like paint on a palette to create our perception of color. However, when we examine the vision systems of other animals, things become quite unusual. Our close relatives, Old World monkeys, have color vision similar to ours, with 3 types of cone cells, but most mammals have only 2, equivalent to our blue and green receptors. Bees also have 3, but they are sensitive to blue, green, and ultraviolet light. Meanwhile, reptiles, fish, and birds may have 4 or more types of cone cells. The small yet fierce mantis shrimp is even more extraordinary, possessing up to 12 different types of color receptors, covering the entire spectrum of the rainbow. The world these creatures perceive is far richer in color than anything we can imagine. Faced with such a diverse spectrum of animal vision, how should we interpret it? For humans, the yellow in a rainbow matches the color of a banana's peel. 826, but for other creatures, strawberries, broccoli, or even human skin might appear the same color as a banana. This reveals a profound truth about reality. Our vision is merely an illusion constructed by the brain. 837, a subjective experience rather than an objective truth. We exist within a visual simulation created by our own minds. Newton revealed the secret of how raindrops and sunlight together form a rainbow. 848, but the colors of the rainbow exist only within our perception. Likewise, the sounds we hear are also illusions, interpretations by the brain of air pressure waves vibrating our eardrums. Everything is subjective. We live in a self-constructed virtual reality. But if what we perceive is not true reality, then what is real? If we cannot fully trust the information from our senses, how can we define the fundamental nature of the universe? At the very least, space and time seem reliable. At the very least, this apple is here right now, a fact that appears undeniable. But is it really? I think, therefore I am. This famous quote from the French philosopher René Descartes has sparked deep reflection on the nature of existence for centuries. Yet Descartes' contributions extend far beyond this idea. On a cold night in 1619, Descartes locked himself in a small room to escape the chill. As a soldier for hire fighting for the Protestant Dutch Republic, he was well versed in engineering and mathematics. But this night was different. Descartes, bedridden with illness, stared aimlessly around the room. He noticed a fly buzzing across the ceiling, eventually landing on the wall. As the fly moved back and forth between the ceiling and the wall, a question formed in Descartes' mind. How could one describe the fly's position? He realized that he needed a reference point to anchor the fly's movements. While the reference point could be arbitrary, it had to remain consistent. He also understood that distance alone was not enough to describe the fly's motion. Direction was equally essential. So, Descartes chose the corner of the room as a reference point, where two walls met the ceiling. From this point, he imagined lines extending along the edges, defining axes that intersected at right angles. By projecting the fly's position onto these axes, he arrived at 3 numbers. These 3 numbers were enough to specify the fly's position at any moment. This was the birth of the Cartesian coordinate system. Today, Descartes' coordinate system is common knowledge. Children learn to use it in elementary school when studying position and motion. For scientists, creating a Cartesian coordinate system is the starting point for solving problems. Descartes' name has echoed through the centuries. Descartes passed away in 1650, unaware of a young boy growing up in the English countryside, Isaac Newton. Newton took the concepts of time and three-dimensional space and used them as the mathematical stage for all motion, formulating the rules of classical mechanics. In Newton's universe, time was absolute. A single clock ticked uniformly throughout the cosmos, and everyone agreed on its ticking. These ideas were reflected in Newton's equations of classical mechanics. Any observer moving at a constant speed could use Newton's 3 laws to predict experimental outcomes. For example, if you drop a ball at a train station, it falls to the ground. If you repeat the experiment on a train moving at constant speed, the ball still falls to the ground. However, if the train accelerates or decelerates, the ball will appear to shift toward the back or front of the train, seemingly contradicting Newton's laws. These fictitious forces only appear when a reference frame accelerates, and they disappear once constant motion is restored. This framework of reality persisted for centuries, until Scottish physicist James Clerk Maxwell unraveled the mysteries of light, revealing the strange nature of the universe. In the mid-19th century, Maxwell unified electricity and magnetism. He realized that light is an electromagnetic phenomenon, an oscillation and intertwining of electric and magnetic fields. His equations also revealed the speed of light, an astonishing 300.000 kilometers per second. But relative to which frame of reference is this speed measured? It seemed that physics required an absolute state of rest to make sense. Some proposed the existence of an ether, a medium through which light traveled across the universe. However, experiments showed that no absolute state of rest exists in the universe, directly challenging Galileo's principle of relative motion. In 1905, Einstein resolved this paradox by introducing the theory of special relativity. At its core, special relativity states that all observers, regardless of their relative motion, must use Maxwell's equations to predict the outcome of electromagnetic experiments. This led to an unsettling consequence. All observers must measure the same speed of light. Thus, Einstein declared that space and time are not rigid or absolute, but flexible. Time and distance depend on the observer. In the 1960s, undeniable evidence of time dilation was discovered. The research focused on a subatomic particle called the muon, which has an extremely short lifespan, only 2 millionths of a second. However, physicists found that high-energy muons could travel tens of kilometers before decaying. This phenomenon could only be explained by Einstein's special relativity, particularly the time dilation effect predicted by the Lorentz factor. Einstein also realized that the speed of light is the ultimate speed limit of the universe, and information cannot travel faster than light. What we see of the sun is actually its state from 8 minutes ago, and the light from the Andromeda galaxy began its journey long before humans walked the Earth. Through telescopes, astronomers observe galaxies as they were billions of years ago. The present state of the universe remains completely hidden from us. Einstein's insights had even deeper implications. Time and space mean different things to different observers. Without Newton's absolute time, there is no universally agreed upon now. The relativity of time means that observers will disagree on the rate at which time flows. This shattered the concept of simultaneity, the idea that two events occurring at different locations happen at the same time. To understand this, Let's look at one of Einstein's thought experiments. Imagine three people sitting inside a fast-moving train carriage. One person stands at the back of the carriage, another at the front, and a third in the middle. The person in the middle emits a pulse of light, which travels toward both the front and the back of the carriage, then reflects back to the center. At the exact moment the light is reflected, the people at both ends raise their hands. To an observer on the train, both hands are raised simultaneously. However, for an observer standing on the platform, since the train is moving, the light reaches the two ends of the carriage at different times. Therefore, the reflections and hand-raising events occur at different times. Simultaneity depends on the observer's perspective. Although Einstein was satisfied with his theory of relativity, he immediately encountered a problem: gravity. Newton's gravitational equation relies on the distance between two masses. But in Einstein's universe, there is no universally defined now, making the concept of a single, absolute distance meaningless. Einstein couldn't fit Newton's gravity into his relativity framework. Ultimately, he had no choice but to completely discard Newton's theory of gravity and redefine it from scratch. In his equations, gravity was encoded in the bending and stretching of the fabric of the universe. After a decade of effort, 1529, Einstein proposed the general theory of relativity in 1915. Using it to explain how gravity works, gravity was no longer a force between two masses, but a feature of spacetime itself. This mathematical framework describes the expanding universe, and the conclusions of Einstein's relativity still hold true today. There is no simultaneity, no universally agreed upon now, and time and space can be dramatically warped and stretched. Whether two things exist at the same time completely depends on the observer's viewpoint. Thus, from the early decades of the 20th century, our understanding of time was forever changed. In Einstein's revolutionary view of the universe, the flow of time is entirely personal. Now, shift your attention back from the distant cosmos. You refocus on the apple in front of you. You are certain that the apple is right here, just a few meters away from you. But now you must accept that your now is only your now. This is your reality, and it belongs only to you. This idea makes you furrow your brow, your thoughts swirling in your mind. The nature of time and place in reality seems like an elusive question. What exactly is matter? This question has puzzled philosophers for centuries. Some objects clearly share similarities. Rocks of various shapes and sizes are all hard, yet their solidity contrasts sharply with the softness of human flesh. They seem completely different, perhaps even fundamentally so. Philosophers once wondered whether nature was infinitely divisible. Could things be cut into smaller and smaller pieces indefinitely? But thinkers from ancient Greece and India proposed a new idea. Everything is made of fundamental building blocks, tiny fragments now known as atoms. The Greek word for atom means indivisible. To ancient philosophers, atoms were the basic components of reality. In the early 20th century, Rutherford assigned two young scientists to explore the structure of matter. Inside a darkened room at the University of Manchester, they peered into the darkness, searching for tiny flashes of light. These flashes indicated that minuscule particles were striking a fluorescent screen. So far, everything was as expected. These two scientists were Geiger and Marsden. Geiger's name would later become legendary due to the radiation detector named after him, but that was still years away. For now, he patiently stared into the darkness, recording every tiny flash. The experiment continued, tracking flash after flash, until one day, Rutherford suggested they look for flashes that weren't supposed to be there. So, Geiger and Marsden dutifully adjusted their experiment and once again peered into the darkness. And at that moment, they forever changed our understanding of physical reality. Rutherford was astonished, calling it the most incredible event of his life. With this new experiment, the atomic world would never be the same. Thomson had already discovered that electrons provided clues about atomic structure. Electrons were clearly negatively charged, meaning there must be a mix of positive and negative charges within the atom. Because, overall, an atom is neutral, the question is, how are these charges distributed? Thomson proposed his atomic model, which we now know as the plum pudding model. This was the atomic model Rutherford was testing in his experiment. He created a beam of alpha particles, positively charged helium nuclei emitted from radioactive elements, and directed them at a thin gold foil. What Geiger and Marsden were searching for in the darkness were the tiny flashes of recoil from these collisions. When alpha particles struck the gold foil, many passed straight through, completely avoiding any interaction with gold atoms. However, occasionally, an alpha particle would collide directly with a single gold atom. Rutherford predicted that these particles would feel a push or pull from the charges inside the atom. slightly deflecting their path. If Thomson's model was correct where atoms were a uniform mix of positive and negative charges, then the deflections should have been minor, causing only slight deviations from the beam. This was exactly what Geiger and Marsden initially observed in their Manchester lab. But under Rutherford's suggestion, they also discovered alpha particles being scattered at extreme angles, far from the beam. Rutherford was astonished. In Thomson's atomic model, such extreme scattering of alpha particles was considered impossible. Rutherford later remarked, "It was the most incredible event of my life." But the question remained, if Thomson's model couldn't explain the scattering of alpha particles, what could? Rutherford concluded that the positive charge in an atom must be highly concentrated rather than evenly distributed. This concentration created a strong electromagnetic repulsion between the atomic charge and the alpha particles. This repulsion was so intense that alpha particles could be deflected in any direction. This led to a puzzling new understanding of the nature of atoms. Rutherford knew that electrons carried a negative charge, and they must be widely dispersed throughout the atom's volume, but they were so thinly spread out that they barely influenced alpha particles. However, since electrons had very little mass, most of the atom's mass had to be concentrated in its positively charged core. Despite this core containing almost all the mass, it was incredibly small, tens of thousands of times smaller than the entire atom. This meant that most of an atom's volume was actually empty space. With Rutherford's insight, Pandora's box of physics was opened. His atomic model shattered our perception of reality and the seemingly solid nature of the world around us. Every chair, every wall, every tree, every apple, all were made of atoms. These atoms combined into countless molecules, defining structure, color, and every other property. But this solidity was merely an illusion. An apple consists of water, vitamins, and acetic acid compounds, yet within each molecule, every atom is actually surrounding the tiny atomic nucleus is a cloud of electrons, meaning that most of an atom is just empty space. Most of an apple is empty, and its solid appearance is merely an illusion. Of course, this isn't just true for apples. Everything that appears solid is the same, including you. It's unsettling, but maybe you can find comfort in reimagining yourself in reality in this way. Maybe it doesn't matter that atoms are mostly empty. They're still made of something, a nucleus and orbiting electrons. These pieces must be real. They must truly exist. But just as physicists once believed molecules and atoms were fundamental, they soon realized that even the mysterious atomic nucleus was far from being the most basic component of matter. As World War I drew to a close, progress accelerated. Once again, Rutherford was at the forefront of discovery, delving into radioactivity and ultimately uncovering the true nature of the atom. Hydrogen, the simplest element, has one positive charge and one electron. Helium has two positive charges and two electrons. Lithium has three, beryllium has four, and so on. Like electrons, these positive charges are identical in charge and mass. Rutherford named these heavy, positively charged particles, protons. Finally, in 1932, after years of theoretical speculation, neutrons were experimentally confirmed. The composition of the atom was finally complete. Initially, the world of matter seemed overwhelmingly complex, with each substance having unique properties. But the realization that all matter was made of just 92 natural elements simplified things dramatically. And with the discovery of protons, neutrons, and electrons, it became even simpler. Every atom of every element and its isotopes were built from these three fundamental pieces of reality. At the outer edges of an atom, electrons zip around at nearly the speed of light. They are tiny, negatively charged particles. At the heart of the atom, 1,000,000 times smaller than an electron's orbit, lies the nucleus, made of protons and neutrons, where nearly all of the atom's mass is concentrated. But as Rutherford's new atomic model gained acceptance, others realized it posed a fundamental problem. It contained a fatal flaw. Critics argued that electrons couldn't stay in orbit. Rutherford's atomic model shouldn't exist at all. The problem stemmed from Maxwell's equations of electromagnetism. These equations stated that accelerating charges must continuously emit energy as electromagnetic radiation. Since orbiting electrons are in constant acceleration, they should constantly lose energy, spiraling inward until they crash into the nucleus. Neither Newton's nor Maxwell's laws of physics could prevent this collapse. In the known rules of reality, nothing seemed to make matter stable. So physicists made a bold decision. They chose to change the rules, and in doing so, they forever altered our understanding of reality.